Hello there! Now we're going to do a business application involving trucks. Here are some facts about semi-trucks and a trip between Columbus, Ohio and Indianapolis, Indiana. Let's see them. Diesel fuel, the type of fuel that trucks use, cost $3.90 per gallon. Interesting. The driver team gets $27 per hour. Running at 50 miles per hour, the truck gets around 4 miles per gallon. That's not very good. Keeping the truck on the road costs $15 per hour over and above the cost of fuel. The trip is 180 miles. Wow. And then we have one more fact. I don't think we have room for it, but I'll put it right here. For each mile per hour increase in speed, the truck loses 1/10 of a mile per gallon in mileage. So it starts off at 4 miles per gallon, but if it goes 51 miles per hour, then it's only going to get 3.9 miles per gallon. All right, with all these facts in our head, we have the question: what average speed will minimize cost? It's not going to be easy, but we should try to get our markers out and draw a picture. Well, it's a little bit hard to draw a picture for this problem, but we're going to try to do it anyway, because it's always a good idea. So let's see. We get our facts out and see if we can incorporate a fact into the picture. So the trip is 180 miles. So maybe down here, this will represent the total distance, and it's 180 miles. All right. And let's see, what else? The driver team gets $27 per hour. So maybe I'll write that up here. Basically, I'm just kind of putting my facts together. $27 per hour. And what else do we know? Keeping the truck on the road costs $15 per hour in addition to all this. So $15 per hour. These are some hourly costs. Let's see. Here, maybe we can draw the truck. If you know what a truck looks like, it looks, well, you might think it looks kind of like this. It's going this way, and it's the wind resistance that causes. So it starts off getting really bad gas mileage, running at 50 miles per hour. So at 50 miles per hour, it gets 4 miles per gallon. But for each mile per hour increase, we will lose 1/10 of a mile per gallon. Okay, and diesel fuel costs $3.90 per gallon. Okay, so we've written down our facts, and just kind of organizing it. Even if you don't think you can draw a picture, oftentimes it helps figure out what's going on. So you should always try to. So here's my picture. Next, we should try to determine our goal. Well, if we look at our picture, what are we trying to do? We're trying to minimize cost with respect to average speed. So we're going to need to write a formula for cost based on this information. So let's see if we can do that. Cost is equal to, well, there are a couple of variables here. So it's, if you recall, it's $27 per hour plus $15 per hour. So it's going to be 27 plus 15 times h. And h is the number of hours that we're on the road. All right, that's fantastic. And fuel cost $3.90 per gallon, right? So 3.90 times G for gallons of fuel needed, and this is our cost. That sounds right. All right, and well, there's no x here, so if x is equal to average speed, then h is equal to, well, the total length of the trip is 180 divided by x. Okay, that's fantastic. That's fantastic. And if fuel costs $3.90 per gallon, then the question is, how many gallons did we use? Well, let's see if we can figure that out. So G is equal to, well, it's going to be equal to 180 divided by our gas mileage, M. And you say, well, why'd you introduce another letter? Well, because M is dependent on x. Remember, M is equal to 4 miles per gallon if we're going 50 miles per hour, and for each mile per hour increase we lose 1/10. And so really, this is the formula for a line. And if you look at this, 1/10, we lose 1/10, so it should be -1/10 is the slope. And then for each mile per hour increase, so it should be 50 is x, and then 4 is our output. And so we have a point slope formula. So M is equal to -1/10. And what are we plugging in? We're plugging in your speed. And so it's going to be x minus 50 plus, how fast are we going at 50 miles? What's the gas mileage at 50 miles per hour? Well, it's plus 4. Aha. So we have, so our goal is to get cost, and we have all this stuff together. Next, we should try to find constraints. Well, in writing down what we wanted, we wrote down a lot of constraints, but there's one more that we can put down. X is going to be our variable at the end of the day, and one of the things I know is that x, the average speed, it's got to be greater than 0 the entire time. Otherwise, you're never going to make it to your destination. Now, we have lots of equations around and lots of letters around, so we should try to solve for a single variable. Well, we've got lots of letters floating around here, but I think we can basically just write down what we have here. So C is equal to, we might as well add 27 and 15, and so that's 42. 42 times, and H is 180 divided by X plus 390 times G. And G is 180 over M times 180 over the mileage. And the mileage is minus 1/10 times X minus 50 plus 4. So there. Now we have a single variable in our equation for cost. Finally, this is a calculus class, so we should try to use calculus to find extreme values. All right, so we've set up our equation for cost, and what we're going to do is we're going to simplify it a bit. So let's look at this. We're going to multiply 42 times 180 to get 7,560. We multiply 3.90 by 180 to get 702. We distribute the -1/10 and that's going to turn our 50 into a positive 5, which we add to 4 to get 9, and our x is then x minus x over 10. So this is our new and improved cost function. Now, since we're looking to maximize this using calculus, we should be looking for critical points, which means we need to look at the first derivative. So we take the first derivative, and what we think here is, I'm thinking of this as 7,560 times x to the minus 1. And so then it becomes minus 7,560 over x squared. The same thing is done here. So I'm thinking about this as 702 times 9 minus x over 10 to the minus 1. So it becomes negative 702 times 9 minus x over 10 squared times the derivative here, which is negative 1/10. There that is, and that's why we have a positive sign here. Okay, now let's look at this derivative. The critical points are where the derivative equals 0 or where the derivative is undefined. This derivative is undefined at x equals 0 and x equals 90. However, as we've discussed, x cannot equal 0. If x equals 0, then the truck will never make it from Columbus to Indianapolis. Could x equal 90? Well, maybe, but something kind of strange happens at 90. The function is undefined at 90 as well. And I think we can even see what's going to happen when x equals 90. If we plug in 89 here, then this number is getting smaller and smaller and smaller, and this number is staying the same size. So this function is going to infinity. So I mean, this is probably not going to be a minimum for cost when, as you approach 90 from the left, the function goes to infinity. So let's see what happens now. So what we're going to do is we're going to set our derivative here equal to 0. So here it is, so it's set equal to 0. And now we have to solve for x. The first thing I want to do is I want to add this term to both sides. All right, there we go. And now what I want to do is I want to, well, since I don't like having these things in the denominator, so I'm going to take the reciprocal of both sides. There we go, that looks nice. And now I'm going to distribute oh, first I'm going to square this term, okay? And so I get 10 times 81 minus 18x over 10 plus x squared over 100. All right, that's fantastic. Now what we're going to do is we're going to distribute this 10. So we're going to get 810 minus 18x, the 10s will cancel, plus x squared over 10. And let's see that. There we go. So now what we're going to do is we'll multiply both sides by 702 and multiply both sides by 7,560. And this is what we get. Notice that the division by 10 goes away here because we get 756x squared. That looks nice. And so now I'll subtract 702x squared from both sides to get 54x squared. These have, I just multiplied these out. And now it's a very nice fact that 54 divides this number and this number, so I can divide everything by 54 to get this nice, fairly simple quadratic equation. At this point, we can use the quadratic formula, and when we do, we get two answers. We get x equals 45 miles per hour, and we get x equals 2,474 miles per hour. We also have x equals 90, but like we said, as we approach 90, the cost is going to infinity. So really, this one's out. And while this is actually a tempting solution, no trucks can go 2,474 miles per hour. So really, the only viable option is 45 miles per hour. Now, if you check, I encourage you to do this on your own. You can check by plugging in 45 to the original equation on either side. You could take the second derivative, but that's going to be actually kind of tough. And you'll see that around 45 miles per hour is in fact a minimum value. And so this is the average speed that minimizes cost. I think this is a really cool problem because we're taking lots and lots of facts, and I know it's a little bit overwhelming, but we're putting these facts together and we're trying to minimize cost. I think it's a fairly realistic problem, at least as far as calculus problems go. All right, time to do some more math.